little pieces of metal don't look like much. But add a shiny coating and a few decorations, and they're worth something. Exactly $1 in Canadian currency. The loonie has plenty of glitter, but no gold. Its nickel core is coated with a copper tin alloy, which is applied by electrolysis. This gives it a gold color. Once the coating is on, these coins will be minted, and they'll end up looking like this. In this program, you will learn that electrolysis is a valuable process in the chemical industry, useful for generating a variety of products and chemicals. You will be able to compare an electrolytic cell to a voltaic cell and evaluate an experimental design for an electrolytic cell. You will learn to construct, observe, and describe an electrolytic cell, comparing predictions and observations. And we'll take a look at some things that glitter, thanks to electrolysis.
Electrolysis and electrolytic cells. Let's find out more about them. To do that, we're going to review voltaic cells, and that's because we can compare and contrast the two. Okay, Robin, here's what we have. It's a Daniell cell, and here's the line notation for it. So, tell me, what's important to have in a voltaic cell?
We need 2 electrodes.
That's right. And which way do the electrons move?
They move from the anode to the cathode.
And that's through the external electric circuit. Well, let's take a look at this actual cell then. Which way are the electrons going? From the
zinc anode through there, and that makes the needle move.
That's right, because the voltmeter shows the direction of current flow, and that's this way, from the anode to the cathode. Good, and then
the cathode, which is the copper.
Okay, what about the chemistry that's going on inside the half cells in this voltaic cell? Well, take a look at the half reactions. First, the cathode.
At the cathode, reduction occurs, and so that would be a gain of electrons.
And that means that the copper 2 ions gain electrons
and become copper solid.
Right. And the other half cell?
At the anode, oxidation occurs, so that's a loss of electrons.
And that means that the zinc in the anode
loses electrons and becomes the zinc ion.
So we should be able to see evidence of that in the real cell. Well, let's take a look at the copper strip. What do we expect to see on the copper strip?
We see the precipitative copper solid.
That's right, and there it is. We're not surprised. And how about the anode?
On the anode, we should see that it should be smaller because it's lost electrons.
And become the ion and gone into solution. Oh, that's great. Okay. We also need something else for a voltaic cell to work.
That would be the electrolyte.
And why do we need that?
Because the cations need to move to the cathode and the anions to the anode, and they do that in the electrolyte.
Right. And the cations are positively charged ions, and the anions negatively charged ions, and they move to ensure electrical neutrality in the cell. What about the porous cup?
We need the porous cup because we need to have 2 different types of electrolyte, but we need to keep them separate while still allowing the ions to migrate.
Okay, and we can show that real easily by taking that porous cup right out of there and have a look at the voltmeter. Well, of course, the voltage drops to nothing because there's no path for the anions or the cations to follow. We put it back in, and there's the voltage again. Okay, well, let's sum this up, and we can do it this way. Movement of ions and electrons results in conduction of an electric current in the voltaic cell. Well, take a close look at what's coming up and see if you can see any major differences between the cell you're going to see and this voltaic cell. Thanks, Robin.
Here's the chemistry that gives the loonie its glitter. When voltage is applied, copper and tin ions from the electrolyte bath gain electrons, are reduced, and deposit on the nickel blanks, which serve as the cathode. Copper serves as the anode and oxidizes at the same rate that copper ions are removed from the electrolyte solution. The result is a bright, shiny blank that will be sent for minting into a coin.
Well, what major difference did you notice?
Well, there was a power supply in the cell we just saw.
Absolutely correct, and that means that the process is called electrolysis, and that the cell was an electrolytic cell. I have one set up right here. We're going to take a look at the similarities and differences between this cell and the voltaic cell we just looked at. So, how are the differences first, Robin?
Well, there's the power supply.
And that's number 1.
Also, there's no porous copper salt bridge.
Good. 2.
The electrodes are made out of the same substance.
And in this case, they're both inert carbon electrodes.
And there's only one type of electrolyte.
That's true, but there are also voltaic cells that contain only one type of electrolyte, like car battery, for example. But in this case, that's correct. How about the similarities?
Well, there are two electrodes,
That's right.
and there is an electrolyte,
That's right.
and there is the external circuit like in the voltaic cell.
Exactly. I think there's a way when we can predict what might happen chemically inside this electrolytic cell. I turn the power on.
If we know what's in it, we can look in the data booklet and use the 5-step method to figure out what's going to happen.
I was hoping you'd say that. So I'll turn this on, and that's exactly what we're going to do. Robin and I have been applying 5-step method to the electrolytic cell we were looking at before. So, what have we done so far? Well, step 1 of the 5-step method says, list the species in the system and identify them as oxidizing agents or reducing agents. So, Robin?
Copper ion, we see, is an oxidizing agent. And the combination of sulfate ion and water is also an oxidizing agent.
Right.
And water by itself can be an oxidizing agent, or it can be a reducing agent.
Okay. Step 2, we identified the strongest oxidizing agent and then wrote the cathode half reaction.
And by going down, we see that that is the copper ion. So we wrote the half reaction.
And we wrote the reduction potential. And where's that?
Right there.
Positive 0.34 volts for that half reaction. Step 3, we identified the strongest reducing agent and wrote the anode half reaction.
So that was water. And we wrote the half reaction.
Okay, and the reduction potential
Was
1.23 volts, but because we had to turn the anode half reaction around from the way it is in the table, we have to write it as a negative value. Okay, step 4 was to write the net reaction.
so we did that by putting these all together.
And what do we have to do to make sure the electron is subtracted out?
We had to multiply this one by 2 because we only had 2 electrons here and we had 4 here.
Okay, and the net potential difference then for this reaction worked out to negative 0.89 volts. And step 5 of the 5-step method is this reaction spontaneous or non-spontaneous? And that's where we're at now.
We could do that by looking on the chart, and we see that the strongest oxidizing agent is lower on the chart than the strongest reducing agent, so we can see it's non-spontaneous.
Right. And there's another thing we have to look at, and that is if the net potential difference value is negative, that's also an indicator of non-spontaneity. So we have 2 ways to find that out, chart and the negative value.
But if it's non-spontaneous, then how did it happen?
And there's the important part of this whole process. In electrolytic cells, we use non-spontaneous reactions, and that's why we need the power supply. Remember the power supply? And the power supply will cause this non-spontaneous reaction to occur against the natural tendency. We add an electric current in there, and we cause this to happen. Now, for this particular reaction, the minimum voltage this current has to have is 0.89 volts. Okay, what about physical evidence that this is actually occurring in our cell?
We should be able to see solid copper on the cathode,
That's right, because here's copper in the cathode half reaction.
and we should see oxygen gas being produced at the anode.
Right, and there it is in the anode half reaction.
And if we use litmus paper, we would be able to see if hydrogen ion was present at the anode as well.
And that's because hydrogen ions are acidic, and they're produced at the anode. So let's go take a look at our cell and see if this has actually occurred. It's time to test the predictions. Here's the cell. It's been operating for a while. Robin, what were our predictions?
We predicted that we should see copper solid at the cathode,
Right?
and that we should see oxygen gas at the anode.
Right?
And we predicted that if we used litmus paper, we would be able to see that it was acidic at the anode.
All right, well, let's take a look at the anode first.
You can see a gas being produced there.
Right, and our equation says that that should be oxygen gas. Okay, now about the acidity. Well, we can't use litmus paper, and I'll tell you why. Litmus paper just says whether it's acidic or not, and not the degree. And it turns out that copper 2 sulfate solution is naturally somewhat acidic. So that won't be able to tell us if any difference has occurred. So what we'll do instead, Robin, is we'll use what's called universal indicator paper. And you take one piece, and I will take a piece, and this is how we'll do it. You test the anode compartment, and I will test some copper 2 sulfate solution, and we'll see if there's been any difference caused by the operation of the electrolytic cell. And so, that should be good. Now let's bring it over to this color chart here and find the color. There, mine is yellowy orange and yours is definitely red. The higher up on this chart that is, the more red the color, the more acidic the solution was. So we can definitely see here that because of your color, the production of the hydrogen ions has caused the anode compartment to be more acidic. Okay, what about the cathode?
We predicted that there should be copper solid on the cathode.
And there it is. And you know, it's called electroplating when you plate one metal to another substance.
Is that the process they use to make gold-plated jewelry and things like that?
It certainly is. And they make a wide variety of things that way. Let's have a look.
In electroplating process, electrolysis is used to coat an object with a thin layer of another metal. Here, a thin shiny coating of metallic chromium is applied over a steel automobile bumper. This makes the bumper attractive and protects the steel from corrosion. Electrolysis is also used to apply gold or silver plating to objects made from less expensive metals. This silver layer is thin, about 0.03 to 0.05 millimeters. And here, electrolysis is used to apply a layer of bronze onto these baby shoes.
Let's now look at the differences between voltaic cells and electrolytic cells. Now, in voltaic cells, electrical energy is produced by a spontaneous reaction. In electrolytic cells, electrical energy is used to cause a non-spontaneous reaction to occur. Now, the connections. In a voltaic cell, the voltaic cell is connected to a meter to register the energy or voltage produced. Now, if we have this voltaic cell connected in series, such as a battery, this energy can be utilized by a flashlight or a motor, a CD player. Now, the connections on an electrolytic cell. Electrolytic cell is connected to an electrical energy source, which provides a minimum voltage. This minimum voltage then is supplying energy for our electrolytic cell to operate. Redox reactions, comparing the two. In a voltaic cell, the redox reactions are anode, the electron flows to the cathode. This causes a spontaneous reaction. In an electrolytic cell, in the redox reactions, we have electrical energy supplied by an energy source to the cathode. At the anode, the electron is withdrawn and returns back to the electrical energy source, which completes the circuit, providing electrons once more to the cathode. So we have to have this continual supply of electrons and the withdrawal of electrons back to the energy source for this non-spontaneous reaction to occur. Now, the electrons supplied have to be of sufficient energy for the reaction to be activated. This is called minimum voltage. The minimum voltage provides enough electrical energy for the non-spontaneous reaction to occur. Now, let's have a look at what we mean by minimum voltage over here. Right now, I have this electrolytic cell operating at minimum voltage. If I turn up the dial and provide more energy, you can see that the reaction rate increases. Look at the bubbles. Now, if I decrease the voltage back to the minimum, we return to our original reaction rate. If I go further past the minimum and drop it below minimum voltage, it would be the same as removing the power supply. The reaction stops. It doesn't occur. Next, we'll see how this process of electrolysis is used by students to produce hydrogen gas.
Ryan, what's the problem?
Well, I was trying to electrolyze some water to make hydrogen and oxygen, but it just wasn't working.
Well, I tell you what, let's review your steps and maybe we can solve your problem. So what did you do?
Well, I was using lab water, and I just filled up this apparatus, and I had a power source.
Which you need, yeah.
And I had an electron flow.
Okay, so the wires were hooked correctly. Now, you said lab water. Which water was that?
That was this water right here.
Well, I hate to tell you that, Ryan, but that's deionized water.
Oh, so we need ions. So
Exactly. Now, if you check under the lab bench, find a solution that we usually use in the demonstration of the Hoffman's apparatus, some sodium sulfate solution. And I'll tell you what, why don't we fill up the Hoffman's and try it again? And I think maybe we'll achieve some success this time.
All right. Pour this in here.
All right, I'll close off. Stop clock's at the top once it's filled. And I'll tell you what, while we're waiting for something to happen after we get it filled, we can predict the reaction equation and see if, in fact, what we expect to happen does happen at the end. There we go, getting close.
Oh, one says going faster.
There we go. A little bit more.
Okay, that looks just about right.
A little more. There we go. Okay.
Okay.
Wonderful. Now, we'll just turn on the switch, and let's get to that prediction. So what technique are we going to have to use to predict this?
Well, I think we'll have to use the 5-step technique.
Exactly. Okay, how are we doing? There we go. Wonderful. Yes, 5-step method. Well, tell you what, why don't we review the steps? What's the first step in this 5-step method?
Well, first we have to list all our species.
Okay. And in this case, sodium ions, sulfate ions, and water. We also have to identify all of the oxidizing agents and the reducing agents. And there we have it. Okay, what's step 2 then, Ryan?
Identify the strongest oxidizing agent and the strongest reducing agent.
Okay, good. Let's go to our redox table here and have a look. First of all, we'll check out our strongest oxidizing agent. So I'll work from the bottom.
Okay.
So there's sodium,
Oh, yeah?
sulfate, and water.
Okay, but... Oh, there's water, so that must be the strongest one.
Exactly. So from our list of 3, water is the strongest oxidizing agent. What about the strongest reducing agent? Working our way down from the top. We find...
Well, water is the only reducing agent, so it must be the strongest one.
Exactly. It's the only one we have, so it has to be the strongest one. So we have an interesting situation here. Water is both the strongest oxidizing and the strongest reducing agent. All right, Ryan, what's our next step?
Write the 2 half reactions.
Good. There's the cathode half reaction showing hydrogen gas and hydroxide ions. And at the anode?
Oxygen gas and hydrogen ions are the products.
Okay, great. Step 4 now, Ryan.
Balance the electrons and write the net reaction.
Good. Okay, so we doubled that cathode half reaction and combine it with the anode half reaction. There's the net reaction. Now, I want to spend a little more time looking at this. If you look at the product side, Ryan, is there anything that you notice?
Well, don't hydroxide ions and hydrogen ions react to produce water?
Right. 4 moles of hydroxide ions added together with 4 moles of hydrogen ions will make 4 moles of water molecules. So, what do we do?
Well, we could just subtract them from both sides, and we have 2 moles of water molecules, making 2 moles of hydrogen gas and 1 mole of oxygen gas.
Exactly. So our net reaction is actually this.
Oh, okay.
Now, let's see if we can determine whether or not what we predicted was going to happen, in fact, did happen. Now, Ryan, you must have had some ideas how we could test whether or not what we expected.
I just thought we could do some diagnostic tests.
Okay, let's review the products at the anode and the cathode first. Okay, here's the products at the cathode, hydrogen gas and hydroxide ions. What tests could we use to see whether or not these were produced?
We could use a burning splint test for hydrogen.
Right,
It should
pop
make a pop.
test. Yeah.
And litmus paper should tell us if we have hydroxide ions, because that's just a base, isn't it?
Mm-hmm.
Okay.
So what would the litmus do then?
Well, it should turn from red to blue.
Great. Okay, and at the anode, we're predicting that oxygen gas and hydrogen ions will be produced.
So a glowing splint should relight in the oxygen gas, and the hydrogen ions should turn the litmus paper from blue to red.
Okay, let's go ahead and see if this happens. All right, let's look at the anode first. And it looks like we've got quite a bit of gas here. So I'll collect the gas and get the splint going, and we'll see whether or not our prediction is verified. Okay, you've got that lit. I'll get the gas. Okay, ready? Blow that out. Okay.
Oh, it relit.
Wonderful.
Perfect.
Great. Okay, now while we're at that particular electrode, let's test the solution that came out of the top and see whether or not there's a color change. And look at that.
Oh, it is.
Our blue turned to a pink color. So our second prediction was verified. All right, let's do the other one here. At the cathode, we predicted hydrogen gas. And while you've still got that splint burning, collect that hydrogen.
Okay.
Okay, ready?
Yeah.
Whoa, a classic pop test. Wonderful. So we have our final test, which is the litmus test at the cathode. So we'll see what happens to this pink paper there. Ah, okay.
Turned blue.
And you can see that the pink paper turned blue. Remember, we had predicted hydroxide ions being produced at the cathode, and the blue color that we see here is a verification of that prediction. So, Ryan, all we needed was an electrolyte in our Hawkins apparatus. Once we had that electrolyte, we had success.
Another important important commercial electrolysis reaction is the electrolysis of sodium chloride solution, or brine. Now here I have a hot apparatus filled with sodium chloride solution. To it, I'm going to add a neutral litmus solution. What we're going to do is make a prediction and then run the experiment to see if we can confirm our prediction by observing. Now, Ryan is going to go and take us through the 5-step method to make these predictions. All right, Ryan, go right ahead.
First, I found all the species involved in the reaction. Those were sodium ions, chloride ions, and water. Water was the strongest reducing agent and the strongest oxidizing agent.
Okay, next.
The cathode reaction was water gets reduced to form hydrogen and hydroxide ions. And the anode reaction was water gets oxidized to form oxygen and hydrogen ions. Now, the net reaction was water is decomposed to form hydrogen gas and hydroxide ions, oxygen gas, and hydrogen ions. And the minimum voltage required for this reaction is 2.06 volts.
Good.
And at the cathode, hydrogen gas and hydroxide ions are formed. Litmus should turn blue in a reaction with hydroxide ions. At the anode, oxygen gas and hydrogen ions are formed, and the litmus should turn red in a reaction with the hydrogen ions.
All right, now let's go over here to experiment to see if we can verify these predictions.
Just put on my safety equipment.
All right, so as soon as you get your gloves on, I'll turn on the power supply, which I've connected up to the cathode and the anode. There you go. All right, this is the cathode. What do you observe at the cathode?
Well, there's a gas being formed, and it seems that the litmus is changing color.
Well, it looks like it's... What color do you think?
It looks like it's turning a little blue.
And what ion does that confirm?
It confirms the hydroxide ion.
Good. Now, let's go over here and have a look at the anode. What do you notice?
Well, there is a gas being formed, but it doesn't seem to be turning red.
Which would confirm the presence of which ion?
Hydrogen.
What color do you see there?
Well, it seems to be turning colorless, actually,
All right.
as far as I can tell.
Now, no hydrogen ion. So what other ions are present?
Well, there are chloride ions and sodium ions.
All right. Now, chloride ion is an ion that's a component of bleach. And bleach can change colors with certain solutions. So this could be perhaps the presence of the chloride ion being shown here. Now, let's go over here to the screen to see if we can determine what's actually happening. Now, two reducing agents, chloride ion and water. Which one did you pick?
Well, I picked water.
And why?
Well, on the chart here, water is lower than chloride ions, so it should be a stronger reducing agent.
All right, so that's logical. Now let's look at the two possible anode half reactions. In this one here, you would predict the evolution of oxygen. Now, the reactions during electrolysis at the electrode surface is very complex, especially in the production of oxygen. Now, what happens is that the sodium chloride solution concentration does actually affect the outcome. Now, the sodium chloride solution is dilute, then water is the strongest reducing agent, and oxygen is produced. If our sodium chloride solution is concentrated, then chloride ion becomes our reducing agent instead of water, and chlorine gas is produced.
So we must have been using a concentrated solution of sodium chloride.
Yeah, we were. It was 2.0 moles per liter. All right, so now let's look at what actually happened. This is our cathode half reaction. Hydrogen and hydroxide was reduced, and we confirmed the presence of hydroxide by the color of blue. Chloride ion was the anode half reaction, and chlorine gas is produced, and you notice that in the Hoffmans it was that clear color. We didn't get the red color that we should have. And in our net reaction, water reacts with chloride ion to produce hydrogen gas, hydroxide ion, and chlorine, and the minimum voltage required is 2.19 volts this reaction. All right, so now this is an exception, and in this case what we actually predicted is not what we confirmed according to our observations. So with the exception of gases such as oxygen, reasonable predictions can be made at electrode reactions.
Chlorine produced in electrolyzing aqueous sodium chloride is a valuable raw material for industries. It's used in manufacturing a large number of consumer products, ranging from simple, rugged plastic plumbing fixtures, pharmaceuticals with complex molecular structures.
Making chlor-alkali chemicals is among the most basic fall chemical processes. Chlorine and caustic soda, or sodium hydroxide, are produced by the electrolysis of sodium chloride water. The reaction is carried out in a large electrolytic cell, such as shown behind me. Electricity is passed through the saltwater solution. Chlorine collects inside the cell at the positive pole, or the anode, and sodium hydroxide and hydrogen is formed at the negative pole, or cathode. Because the reaction yields chlorine and caustic soda in nearly equal amounts, they are called co-products. Hydrogen is a byproduct. Sodium chloride salt, which is the same as table salt, is the only raw material used to make chlorine and sodium hydroxide. About 1.5 kilometers below the surface is a large salt deposit. In fact, this is the main reason why Dow Chemical is settled on this site. In order to mine it, water which is recycled from the plant and river water is injected down into the cavern. The water dissolves the salt, and the brine solution is then pumped to the surface and stored in ponds. From the ponds, the brine is pumped to the electrolytic cells where direct current electricity is passed through the brine. We use approximately 175 megawatt hours of electricity, which is equivalent of the consumption of a city of 60,000 people would use. Chlorine leaves the electrolytic cell as a hot gas. First it is cool, and then the water is removed in a drying train, which is a series of towers where we counterflow the gas with sulfuric acid, which absorbs all of the water. The chlorine is next compressed and then liquefied by cooling it to about -30°C. It is then stored in our chlorine sphere. Over 90% of the liquid chlorine is then re-vaporized and used on site as one of the raw materials to produce vinyl chloride monomer, which is then made into PVC plastic. The remaining chlorine production is loaded into tank cars and primarily shipped to the pulp and paper industry.
As a strong oxidizing agent, chlorine provides an important tool for safeguarding the public health. Chlorine's oxidizing power makes it deadly to bacteria. Because of this, the chlorination of public water supplies, swimming pools, and sewage has helped to eliminate many public health threats. Chlorine is used in a form other than gas in these applications. This is because chlorine gas is deadly to humans. It was one of the poisonous gases used in the trench warfare of World War I.
In today's program, we learned about electrolysis. We looked at the similarities and differences between an electrolytic cell and a voltaic cell, and applied this knowledge to evaluate an experimental design for an electrolytic cell. We learned to construct, observe, and describe an electrolytic cell, comparing predictions and observations. We saw how electrolysis is used to generate a variety of products and chemicals, and to add a shiny protective layer through electroplating, a layer that glitters and may or may not be gold. Okay, let's sum this up. I think we can do it this way. Movement of ions and electrons result in
We turn to our original reaction rate. Next, we'll see how the process of it.
And the reason for that is so that electrical neutrality is kept in the cell. That's done by the positive ions, the cations, moving to the cathode, like you said, and the negative ions, the anode, moving to the anode. Okay.